What if the next generation of rockets didn't land upright at all? Imagine a Starship diving through the thin Martian sky, then flipping sideways, firing engines from its sides and touching down like a massive steel airplane. It sounds insane, right? But believe it or not, this wild idea, side-mounted engines and horizontal landings, has been seriously discussed inside the space community. The question is, could it actually work? Or would it break every rule of rocket engineering we know? Find out everything in today's TechMap episode. Have you ever wondered why Elon Musk has such a big issue with landing legs? Simple. They add weight, they complicate the design, and they create more points of failure. But here's the thing, without landing legs, a rocket has nothing to steady itself on touchdown. It would just topple over. So at first glance, legs seem absolutely necessary. But Musk, he doesn't think inside that kind of box. When everyone else saw legs as the only way, he went full outside the box and came up with something wild, a massive steel tower with 2 robotic arms that literally catch the booster out of the sky. That's right, Mechazilla. Now that's an awesome solution for launches on Earth, but it immediately sparks a bigger question. Could we ever pull something like that off on the Moon or Mars? Let's strip this problem down to first principles. How should Starship land on other worlds if legs aren't an option? Back in the early days of Starship's development, Musk actually pitched a radical idea. Instead of traditional legs, why not use the ship's own body as a landing surface? The concept was for Starship to descend vertically and then gently tip over just before touchdown using a deployable composite landing pad to distribute the force and keep things stable. SpaceX even included this concept in their proposal for NASA's human landing system. But NASA wasn't exactly sold on it. They wanted the safer, more familiar option of vertical landings, with legs especially for crewed missions. Still, that wild horizontal landing idea stuck around, and it kind of blew up online. The space community ran with it, brainstorming all kinds of creative versions. One viral clip even showed a Starship with 4 side-mounted Raptor engines designed to let it shift orientations mid-descent for a smooth horizontal landing. So what makes this kind of sideways or horizontal landing concept actually appealing? Well, for starters, it spreads out the landing forces across multiple points on the rocket's side. Think of it like giving the rocket a wider stance. That extra balance helps keep it from tipping over during touchdown. There's another cool advantage too. By placing engines along the sides, you can lower the rocket's center of gravity. It's kind of like how a sports car stays stable through sharp turns because it sits lower to the ground. In theory, this makes the rocket less wobbly and easier to stabilize when it's coming in for a landing if it's designed right. Now that's something bottom-mounted engines just can't do. Traditional rockets push straight from the bottom, so all that landing force travels down one narrow point. The legs have to absorb everything, all the impact, all the weight, and still keep the rocket upright. That's a big ask, especially on worlds with an atmosphere like Mars, where the rocket has to fight drag and angle itself just right during descent. But here's where the big question kicks in. Is this sideways landing approach actually feasible? Could Starship really pull it off? Some people think so, and their reasoning is pretty clever. They point to Starship's flap hinge points, those massive, super strong joints that hold the big aerodynamic flaps on each side. When Starship is flying through Mars's thin atmosphere, it's slammed by sideways forces of over 400 tons on those hinges. That's enormous, but they're built to handle it. So if those hinge points are already designed to take huge side loads, why not mount engines there? In theory, SpaceX could install small Raptor engines or thrusters at those hinge points using the existing structure to handle the landing stresses. It's a wild idea, but not impossible. Now, if we move this concept to the Moon, things get even easier. The Moon doesn't really have an atmosphere, which means Starship wouldn't experience those massive sideways forces during descent. Because of that, Engineers think the lunar version of Starship, especially the HLS version for NASA, might not even need heavy reinforcements. Its current structure could probably handle the landing just fine, maybe with only minor tweaks. And it's not like side-mounted engines or some sci-fi fantasy. We've actually seen similar systems before, just on smaller scales. The Space Shuttle, for example, had 6 tiny vernier thrusters to help it adjust its orientation in space. Even NASA's Space Launch System uses a mix of big bottom-mounted main engines and smaller auxiliary thrusters around the body for control. Now, here's the catch. All those side-mounted engines and thrusters we've talked about, they've only ever been used as support systems, not for the main lift or landing of a spacecraft. And there's a good reason for that. See, when engines are mounted on the sides, they create uneven pressure on the rocket's structure. Instead of pushing straight up, they push from an angle which bends the rocket a bit, kind of like when you press on one side of a ruler and it flexes. That bending causes what engineers call structural stress. To handle it, the rocket's body has to be built much stronger, and that usually means heavier. It doesn't stop there. The fuel lines and control systems for side-mounted engines get way more complicated. You've got to route propellant differently, manage thrust vectoring in new ways, and keep the rocket balanced while it's firing sideways. All of that adds complexity and potential failure points. And when it comes to landing or takeoff, that imbalance becomes a real challenge. If your engines aren't pushing straight up, it's a lot harder to keep the rocket stable during descent, one small error, and you're tipping over. So in the end, the classic design bottom-mounted engines still wins. It's simple, it's proven, and it just works. But hey, that doesn't mean the idea of a side-thrusting Starship isn't exciting. Imagine a future Starship variant with Raptors mounted on the sides. It sounds insane, but also kind of awesome. Right? So what do you think? Should SpaceX or maybe another company actually try this out someday? Drop your thoughts in the comments below. I'd love to hear what kind of crazy next-gen landing systems you think could work for future space missions. Not only the side-mounted engine, but also the horizontal landing position in general is not popular. Most engineers and space fans agree that while it sounds futuristic, the trade-offs might completely outweigh the benefits. The biggest concerns: mass complexity and practicality. Let's start with mass. To land a rocket horizontally, you'd need extra hardware. As said, things like stronger structures to handle bending forces from side engines and additional systems to manage thrust from different angles. But it doesn't stop there. Horizontal landing often requires extra fuel tanks that are dead weight until they are used at the very end of the mission, which are way heavier than aero flaps. It is mainly because the rocket needs more fuel to control its fall and keep flying sideways or tilted like an airplane before it actually lands. Unlike vertical landing, where the rocket just fires engines straight down to slow its speed, horizontal landing uses wings and control surfaces to glide and slow down over a distance. This means it stays in the air longer and needs fuel to keep engines running or to adjust its position during that glide. Also, horizontal landing designs usually have bigger wings and control parts that take up space and weight. So extra fuel tanks are needed to carry enough fuel for the longer, more complex landing process. And then there's the engineering side. To support a design like that, you'd need major structural reinforcements enough that by the time it's all practical, you might as well have built a completely different vehicle. Somebody even compares this to a Toyota Corolla, which is designed for smooth city roads, not rough off-road trails. Someone might ask, why can't we just raise the Corolla's wheels and take it off-road? But to do that properly, you have to add stronger suspension, bigger wheels, tougher tires, better clearance, and maybe a stronger frame until it becomes more like a Toyota Tacoma, a truck built specifically for rough terrain and off-road conditions. And of course, extra structure means extra cost. More mass means more refueling missions, less room for crew or cargo, and higher operational expenses. You'd also lose the landing commonality that SpaceX relies on. Different versions of Starship would need totally different landing systems, adding more complexity to the entire fleet. Then there's the control problem. One user on Reddit commented, "Engines placed so far from the horizontal center of mass would need to be very fine-tuned to prevent pitching. A little bit of unbalanced force with such a long lever arm creates a very drastic difference. Most importantly, the fuel could slosh a lot more in a horizontal fuel tank. I know the tanks have anti-slosh baffles, but they may not be effective enough. And the internal layout becomes another headache. Do you still keep crew space on one end and fuel tanks on the other? If so, balancing the entire ship during a horizontal landing gets even more complicated." Some defenders of the idea say, well, Starship already handles huge lateral loads during re-entry, so what's the difference? But engineers point out it's not the same thing. During re-entry, the aerodynamic pressure is spread evenly across the hull. It's a distributed load. But during a horizontal landing, those forces are concentrated at just a few points, like engine mounts, creating intense localized stress that the structure simply wasn't designed for. SpaceX specifically avoids putting engines near the lunar surface because of this. Lunar regolith isn't soft powder. It's made of sharp glass-like particles that can blast out at high speeds, damaging equipment and coating everything nearby. That's why the HLS version of Starship uses high-mounted thrusters to steer clear of the dust. Switching to a horizontal landing doesn't solve this. In fact, it could make it worse by blowing dust sideways instead of straight down. NASA's Human Landing System, HLS program, is working with 2 U.S. companies to develop landers that will safely carry astronauts from lunar orbit to the surface of the Moon and back throughout the agency's Artemis campaign. SpaceX for Artemis 3 and Artemis 4, and Blue Origin for Artemis 5. Beginning with Artemis 3, the lander will be launched uncrewed to lunar orbit to wait for the crew. Launching atop NASA's SLS, Space Launch System rocket, the Orion spacecraft will bring the astronauts from Earth to the lander in lunar orbit. A crew of 2 will transfer to the lander from Orion and descend to the Moon's surface. For later crewed missions, astronauts will use NASA's Gateway Lunar Space Station for crew transfer. You've probably heard people talking about a new space race, and this time it's not the US versus the Soviet Union, it's America versus China. But here's the surprising part: experts say the US might actually be at risk of falling behind. So, what's going on? According to many space insiders, the biggest culprit is NASA's Artemis program, the initiative that's supposed to take astronauts back to the Moon and eventually to Mars. Sounds epic, right? But there's a catch: the program's complexity is becoming its biggest weakness. At the heart of Artemis are 2 key pieces of technology: the Space Launch System SLS rocket and the Orion spacecraft. Both are incredible feats of engineering. But they also come with major baggage. They rely on older tech, have a history of technical challenges. And maybe worst of all, they're funded under cost-plus contracts, meaning contractors get reimbursed no matter how much things cost or how long they take. That system might have worked decades ago, but today it's creating massive delays, budget overruns, and uncertainty. Meanwhile, China's space program is moving fast, using a much more streamlined and focused approach that could put them ahead in the race to build a permanent lunar presence. Now, NASA isn't publicly admitting that SLS and Orion are slowing things down, and they're definitely not planning to ditch them, at least not yet. Instead, they've turned to their private partners, SpaceX and Blue Origin, asking them to come up with ways to speed up the human landing system, the critical piece that will actually land astronauts on the moon. Neither company has revealed exactly how they plan to do it, but the space community is buzzing with speculation. The consensus: NASA should eventually phase out SLS and Orion entirely, yes, seriously, and lean more on commercial spacecraft like SpaceX's Starship or an upgraded Crew Dragon. These next-gen vehicles are built for reusability, run under fixed-price contracts, and offer a faster, cheaper, and more efficient path forward. There are a number of different mission architectures that could involve Starship and Dragon, one of which I think is quite interesting, which is to put the Dragon spacecraft inside Starship. Yeah, you heard that right. We launch a Crew Dragon into orbit, and then either stash it inside the lunar Starship or dock it to the front. From there, Starship would carry the Dragon all the way to lunar orbit, drop it off like a cosmic taxi, and after the surface mission, the astronauts would climb back into the Dragon for the return trip home. Now here's why that idea is so fascinating and actually pretty practical. Starship's massive payload capacity, over 100 tons to low Earth orbit, means it could comfortably haul not just a Dragon capsule, but also a kick stage to push the combo toward the moon. Once in lunar orbit, Dragon takes over for the ride home. This mission architecture offers some serious advantages over NASA's traditional Artemis approach. First, the Crew Dragon only needs to provide about 450 meters per second of delta V. That's just enough for the journey from lunar orbit back to Earth. That's a relatively tiny propulsion requirement compared to what a full lunar mission would demand. Second, Dragon's life support system doesn't need massive upgrades. It's already designed to support 4 astronauts for around 4 days. And conveniently, that's about how long the trip from lunar orbit to Earth takes, 3 to 4 days. So the existing systems for oxygen water power and CO2 scrubbing would likely be enough with only small tweaks. Here's what that means in practical terms. No major increase in oxygen or water storage. Life support remains pretty similar to what's already proven on Earth orbital missions. Only minor thermal protection upgrades would be needed to handle the higher re-entry speeds from the moon. Consumables like CO2 scrubbers might just need simple replacements instead of a total redesign. Power systems might get a small battery upgrade, but nothing too crazy. And here's a clever twist: those Super Draco engines on Crew Dragon, originally meant for emergency aborts, could potentially be repurposed for reaction control and orbital maneuvers around the moon. That means even fewer modifications are needed to make Dragon deep space ready. Of course, carrying a 12-ton Dragon inside Starship does eat into Starship's payload, dropping it from roughly 50 tons to about 38 tons on the lunar surface. But considering NASA's current HLS requirement is only around 1 ton, that's still massive overcapacity. So in theory, this hybrid Starship Dragon mission could give NASA a faster, cheaper, and more flexible way to land humans on the moon, all while using mostly existing flight-proven hardware. Honestly, if SpaceX ever decides to test something like this, it could redefine what we think a lunar mission looks like. Okay, so we've talked about the idea of sending a Crew Dragon inside or attached to Starship for a lunar mission. But let's be real. Crew Dragon was originally built for low Earth orbit missions, so if we're sending it all the way to the moon, a few key upgrades would absolutely be needed. First up, the heat shield. Crew Dragon's heat shield is made from Pica X, a high-performance material that's actually capable of handling the extreme heat generated when returning from lunar velocities. The problem isn't the material itself, it's the thickness. Right now, the shield isn't thick enough for a full lunar return because of weight constraints. To make it moon-ready, SpaceX would need to thicken the Pica X ablator layer and reinforce the structure that bonds it to the capsule's frame. That means stronger backing materials, improved bonding, and possibly even new design tests to ensure the shield can survive longer, hotter re-entries from deep space. Now SpaceX already has experience here, After noticing some erosion on early Crew Dragon heat shields, they made several reinforcement upgrades. So a more advanced iteration of that same process could prepare Dragon for lunar missions, especially if they want it to be reusable for multiple deep space returns. Next, let's talk about Starship, because carrying Crew Dragon, whether inside or on top, comes with its own serious engineering challenges. Here's what SpaceX would likely have to modify. Structural reinforcement Starship's payload bay or nose section would need to be strengthened to safely hold Dragon's 12-ton mass, especially during launch, when vibrations and aerodynamic forces are at their peak. Aerodynamics. If Dragon is mounted externally, SpaceX would need to design a protective fairing or aerodynamic shroud to reduce, drag, prevent buffeting, and shield the capsule during ascent through the atmosphere. Docking and integration systems. Starship's interface ports would have to be reworked to fit Crew Dragon's docking hardware. That means new attachment points, custom deployment mechanisms, and safety systems to handle separation or redocking in different mission phases. Thermal protection. The Starship surface near Crew Dragon would need extra heat shielding to manage the localized aerodynamic heating during ascent. Internal configuration. If Crew Dragon rides inside Starship, engineers would have to redesign the internal layout to keep it secure, while still allowing easy access for pre-flight checks and integration. All these adjustments are crucial to maintain safety margins and mission reliability, since we'd be combining two spacecraft that were originally designed for completely different purposes. One for Falcon 9 launches the other for a fully reusable two-stage system. Integrating them would require deep structural, thermal, and aerodynamic analysis, plus rigorous testing to prove the concept works. But here's the thing. If there's any company that can pull this off quickly, it's SpaceX. Their rapid design, test, iterate approach means they could prototype, test, and refine these changes in record time. All right, so the idea of sending a Crew Dragon inside Starship for a lunar mission sounds awesome. But not everyone's convinced. In fact, some people in the space community say this whole concept might actually be impractical. Let's break down why. First off, the landing and return problem. If you only launch one Crew Dragon capsule, the mission basically turns into a wave hello to the moon as you fly by scenario. That's because Crew Dragon simply can't land on the lunar surface, at least not in its current form. Now, SpaceX once had a similar concept called Red Dragon, which was supposed to land on Mars using supersonic retro propulsion. Here's how that would have worked. After entering the atmosphere at supersonic speeds, the capsule would fire its Super Draco thrusters to slow down, skip the parachutes entirely, and then use retractable landing legs to touch down softly. It was bold, innovative, and incredibly complex. NASA considered it too risky for crewed missions because propulsive landings would require years of testing and certification to meet safety standards. Basically, you'd need to re-engineer almost the entire spacecraft just to prove it could safely land with humans aboard. And that's exactly what critics say would happen here, that modifying Crew Dragon for a lunar mission would mean designing, engineering, and building an entirely new spacecraft. Then there's the return issue. Right now, Crew Dragon can't make the trip home from lunar orbit. Even with upgrades, integrating it with Starship introduces a ton of new challenges that SpaceX has never faced before, and none of these modifications are part of Starship's current development roadmap. If Dragon is mounted on top of Starship, it could in theory still use its abort system, but that would completely change Starship's aerodynamics and launch profile, meaning SpaceX would have to redesign major parts of the rocket. If placed internally, adapters would be required to allow fuel lines and other volatiles to pass through the Starship's walls, and it doesn't stop there, even launch infrastructure would need to change. The Starship launch tower would have to be modified with dedicated fueling and loading systems, like those used for Crew Dragon's Falcon 9 setup. That's a massive logistical headache. So when you add up all the design work, testing, and infrastructure costs, many experts argue the idea just doesn't make economic sense. The costs and time required to make this hybrid system safe and functional would outweigh any benefits. On November 5th, after completing a 6-month mission aboard the Tiangong space station, 3 Chinese astronauts were ready to return home. But their descent was suddenly postponed. The reason engineers believed the spacecraft might have been struck by space debris. Since that moment, teams on the ground have been running continuous simulations, safety checks, and system tests. Every system has been analyzed, every response rehearsed. What makes this case remarkable is the openness surrounding it. China has publicly confirmed the incident, something rarely seen in its space program. That level of transparency suggests just how serious the situation might be. But how dangerous can a small piece of space debris really be? Space might look vast and empty, but in low Earth, orbit speed changes everything. Objects travel at about 8 kilometers per second, almost 28,000 kilometers per hour, faster than a bullet. At that velocity, even a 1 millimeter fragment of metal can release more energy than a gunshot. Now imagine what happens when that fragment hits a spacecraft. The result can range from a minor surface impact to catastrophic damage. And this isn't the first time such threats have appeared. In 2023, a solar panel on China's space station was damaged. A year later, astronauts had to perform spacewalks to install extra protection. Now, in 2025, the Shenzhou 20 finds itself caught in the same danger. This problem isn't unique to China. In 2021, SpaceX's Crew Dragon capsule had its own close call when a piece of debris passed near it during the Crew 2 mission. NASA and SpaceX reacted swiftly, instructing astronauts to secure themselves in the capsule. The debris missed, but it was a reminder of how fragile safety in orbit truly is. Both the Shenzhou 20 and Crew Dragon incidents reveal the same truth: low Earth orbit is becoming a minefield. No matter how advanced our spacecraft are, the risks remain. It's like driving through a storm of invisible shrapnel. No one is ever completely safe. Yet the Shenzhou 20 situation also highlights a deeper difference between nations. The United States relies heavily on much more advanced systems equipped on Dragon that constantly track and predict debris paths. China's systems are still developing, facing both technical and political challenges. The result is a contrast in how each nation prepares, responds, and shares information in the face of one of space's growing dangers. The U.S. operates a vast network of radars and telescopes spread across continents and orbit. These instruments scan the skies every second, tracking hundreds of thousands of pieces of debris. NASA, together with the U.S. Space Force, maintains one of the most detailed catalogs of objects circling Earth, sharing that data with partners like SpaceX and other international agencies. This network enables highly accurate predictions and the ability to avoid danger before it strikes. China's tracking network is smaller and more centralized. It relies mainly on its domestic telescopes and a growing fleet of sensors in low Earth orbit. Its Space Situational Awareness System is designed primarily to protect Chinese satellites and the Tiangong space station. However, its global coverage is more limited. Even so, China has been steadily expanding its capabilities, working on new sensors and building stronger links with international partners. The Tiangong station itself plays a central role in this effort. It is fitted with instruments capable of detecting debris larger than 10 centimeters. The crew of Shenzhou 20 has taken part in 4 spacewalks focused on reinforcing the station's shielding, an effort that began after a 2023 incident when a piece of space debris struck a solar panel and caused a temporary power loss. Engineers later installed new layers of protection on Tiangong's outer structure to defend it from future impacts. Still, China's approach remains more focused on passive defense, building stronger shields and reinforcing spacecraft, while the United States and its partners rely on proactive maneuvers to avoid collisions altogether. NASA and SpaceX use continuous real-time tracking, supported by data from the U.S. Department of Defense and allied space networks. These systems allow SpaceX's Crew, Dragon, and Starlink satellites to automatically adjust their orbits using thrusters, steering clear of predicted debris paths before they become a threat. Each maneuver is carefully planned in coordination with NASA Mission Control, ensuring safety without interrupting ongoing missions. Aware of the limits of current technology, China is now investing in active debris removal systems, concepts that include robotic capture, towing, and controlled deorbiting. But such missions are costly and complex, and still in the early stages of development. In the United States, SpaceX is also studying cleanup technologies, exploring bold ideas such as using its Starship vehicle to capture or redirect debris using nets, harpoons, or lasers. Both nations enforce strict debris mitigation rules. China requires its spacecraft to deorbit or lower their altitude at the end of their missions. SpaceX, meanwhile, designs its rockets and capsules to return safely to Earth, minimizing leftover debris. When the Dragon spacecraft re-enters the atmosphere, it uses advanced guidance systems to slow down, steer, and land precisely. Most components either burn up completely or splash down gently for reuse. This approach not only preserves hardware, but also keeps Earth's orbit cleaner and safer for future missions. For short, China's network is advancing, but it lacks the large-scale automation and global maneuvering capabilities already integrated into NASA and SpaceX systems. That gap helps explain why incidents like the Shenzhou 20 emergency have become a growing concern. For China, the challenges are not purely technical. Cost remains a major factor. A single debris removal mission can cost anywhere between $100 million and $500 million. NASA estimates that using lasers to nudge debris out of orbit could run as high as $1 billion per system. Every method, whether robotic arms nets or propulsion systems, requires precision fuel and time. There are also national security concerns. China closely guards its space data, wary of revealing technologies that could have military applications. Much of what protects satellites can also target them, so secrecy remains a strategic choice. The downside is reduced international cooperation and less access to shared debris tracking data. In the United States, laws like the Wolf Amendment restrict NASA from working directly with China on space projects without special authorization. The goal is to prevent sensitive technologies from being transferred. Yet this separation has also led to two very different systems evolving side by side, one built on secrecy, the other on collaboration. Of course, an incident like this cannot be left to mere technicalities. It immediately sparked a heated debate online about who was responsible. One of the first lines of thought to emerge was historical irony. Many recalled China's 2007 anti-satellite missile test, which created thousands of pieces of debris. The question is whether they themselves are the victims of the space junk they created in the past. There are also more optimistic views. They hope that this will be a wake-up call. When they themselves become victims, perhaps China will become more serious and even take the lead in solving the problem of space illusions. But there is no shortage of harsh criticism. They argue that based on statistics, China is one of the countries that produces the most space junk. So according to them, this is not a random accident, but a foreseeable consequence. And of course, there is a bit of skepticism. Some people hypothesize whether the cosmic accident is just a perfect cover that comes in handy for any other potentially embarrassing failures. Because the cosmic accident is unpredictable, it is very difficult to verify. I'm not saying it wasn't a piece of debris, but that can also be a convenient cover for other mishaps. The last time damage in space was blamed on impact from space debris, a second spacecraft suffered the exact same damage. Orbital debris cannot be predicted, so it's a perfectly useful cover for any other potentially embarrassing failure. So what's your take? Do you think space junk is just a perfect excuse? In this case, let me know in the comments. You know, I'm so interested in conspiracy theories. This debate also raises another issue: media attention. Some people have commented that the Tiangong space station, such a major technological achievement, has barely been mentioned in the Western media until something bad happens. And here is an interesting statistic compiled. It shows the number of articles about Tiangong in November. Newspapers in Hong Kong, like the South China Morning Post, have reported a lot, but major newspapers in the US have less. Meanwhile, no newspapers in the UK or Australia have reported it. This shows that our view of space is also influenced by a geopolitical prism. Okay, so after all the blame shifting, the most important question is, what can we do? Fortunately, the discussion has moved beyond criticism and into finding practical solutions. There are three main directions that have been put forward. One is the standardization of technology, specifically docking ports, so that ships from one country can rescue ships from another. Two is the global law, which requires clear international regulations to limit the creation of additional space junk. And three, perhaps the most difficult, is to be the one to clean up the trash. The first idea and standardization of technology already exist. It is called IDSS. It can be imagined as a standard USB port for all spacecraft. Both the ISS and Tiangong have adopted this standard. It allows ships from different countries to connect to each other in case of an emergency. Remember that dramatic mission in June 2024? Astronauts Butch Wilmore and Suni Williams came dangerously close to disaster when Starliner's thrusters malfunctioned during approach to the International Space Station. Those issues stranded them in orbit for months. Although Starliner did eventually dock, NASA wasn't taking any more chances. After an intense review, the agency told Boeing, "You're bringing that vehicle home, but it's coming back without humans on board." To fill the gap, SpaceX launched a Dragon mission in September 2024, carrying just 2 astronauts instead of 4, ensuring Wilmore and Williams could safely return home in March 2025. So, what actually caused those thruster issues? NASA and Boeing eventually traced it to overheating in tiny Teflon seals inside the thruster valves. These seals were breaking down, disrupting performance. The good news? They not only identified the issue but also managed to recreate the exact failure on the ground, which is huge for understanding the fix. Now, Boeing's next test, Starliner 1, will be all about proving that redesigned thruster system before astronauts ever climb aboard again. In other words, this next flight is like Starliner's training pants mission, a prerequisite to achieving full certification for manned operational missions. Even though Boeing is shifting toward a cargo flight right now, their ultimate goal hasn't changed, completing certification to carry crew to the ISS. The original commercial crew contract, signed back in 2014, called for 6 operational missions once certified. But after all the changes, the updated plan looks a little different. After Starliner 1, there'll be 3 crewed missions, but only after the spacecraft is certified safe. Starliner 2, 3, and 4, before the ISS retires. There's technically funding for 2 optional flights after that, but with the station nearing its end of life, those are looking unlikely. If you're counting, that means Boeing's total Starliner manifest now stands at 7 flights. 3 test flights, 1 uncrewed, Starliner 1. and 3 crewed missions to follow. This contract reshuffle also affects Boeing's launch partner, ULA. Boeing originally bought 9 Atlas V rockets, but with fewer missions now, a few of those launches might end up going unused. NASA's holding on to them as options for now, but there's talk they could be sold to other customers, maybe even Amazon, which has been snapping up Atlas Vs for its Kuiper satellite project. Now, here's the part that really puts Boeing in a tough spot: the money. The Starliner program has become a financial black hole for Boeing, with losses climbing to more than $2 billion. That's right, billion with a B. Why? Because of the contract. NASA's Commercial Crew Program runs on a fixed-price model, meaning NASA pays a set amount for each milestone, no matter how long or how expensive it gets for Boeing to complete it. So when Starliner hit delays, redesigns, and extra testing, Boeing had to foot the bill themselves. Every time they missed a milestone or had to rework a system, that was money out of Boeing's pocket, not NASA's. This setup has been described inside Boeing as nothing short of disastrous. Here's the brutal reality. Boeing has already logged multi-billion-dollar losses on Starliner across several financial quarters. Those funds are gone. They're what business folks call sunk costs. But despite bleeding money, Boeing can't just walk away. The company is still obligated to fulfill its contract with NASA, unless NASA itself decides to make a change. And no one really knows how much more that's going to cost. At this point, Boeing's best bet might be to limit further losses, maybe even break even on those last few flights. Quitting now would not only leave money on the table, but also deal a massive blow to Boeing's reputation in spaceflight. So even though Starliner isn't likely to have a life beyond the ISS era, Boeing might be playing the long game. They could still market Starliner to future private space stations, like those being built by Axiom or Starlab, where having a second crew transport option besides SpaceX would be valuable. From that angle, continuing Starliner makes sense, even if it's painful in the short term. But this whole situation might permanently change how Boeing approaches government contracts. After what happened with Starliner, insiders say Boeing's management has no intention of ever touching another fixed-price contract again. Instead, they'll likely stick to what's known as cost-plus contracts, where NASA or the government reimburses all expenses plus a profit margin. That's a huge contrast between old space and new space. Traditional aerospace giants like Boeing and Lockheed Martin have always operated in that cost-plus world, where risk is low but innovation is slower. Meanwhile, SpaceX has mastered the fixed-price approach, betting on efficiency, vertical integration, and fast iteration to keep costs under control. That's one of the biggest reasons SpaceX has been able to move so fast, while Boeing has struggled to keep up. Now, here's the interesting part. While Boeing's been dealing with technical issues and billions in losses, NASA hasn't given up on Starliner. And honestly, that decision makes sense from a strategic point of view. You see, right now, NASA only has one American-made spacecraft that can take humans to orbit, SpaceX's Crew Dragon. If something ever grounded Dragon, or if SpaceX shifted fully to Starship, NASA would be left without a reliable, US-based backup for crewed missions. That's not a position NASA ever wants to be in. So even though Starliner's been a rough ride financially and technically, NASA still wants to certify it, because having two independent systems increases both safety and competition. Plus, as said, if Boeing eventually gets Starliner working, it could find new life flying crews to future commercial space stations. Not every private company wants to rely solely on SpaceX, and Starliner could give them a second option. And here's where Starliner actually has a unique advantage. It's what engineers call launcher agnostic. In theory, Starliner could be launched on different rockets, not just the Atlas V it's using today, but possibly Vulcan, or even Blue Origin's New Glenn down the road. That flexibility could become extremely important if SpaceX retires the Falcon 9 and moves everything over to Starship. Because here's the thing. If SpaceX stops flying Falcon 9, there might be no rocket left that can carry Dragon. That raises some big questions. Would SpaceX spend the time and money to redesign Dragon to fly on another rocket like Vulcan or New Glenn? Or would they just move fully to Starship, even if that means no certified human-rated spacecraft for years? It's a fascinating what if, and it's why some people inside the space community are saying NASA should make a serious effort to certify Starliner with Vulcan at a minimum. That said, the future of Starliner is still very uncertain. Let's be honest, it hasn't had a single fully successful mission yet, while SpaceX's Crew Dragon has already completed 11 NASA's operational flights to the ISS. Dragon's proven itself to be modern, safe, and cost-efficient. Starliner, on the other hand, has gained a reputation, and not a flattering one. Some in the space community have flat out called it a money black hole, or even a complete disaster. One frustrated commenter summed it up perfectly. At this point, it seems like a big waste of taxpayer money for 4 missions then ISS goers splash. I cannot fathom any reason other than Boeing tears to keep this shit show going. He even joked, rather brutally, hell, by the time anyone, nation or business, attempts to put another station in orbit, Starliner will resemble a Model T compared to anything that can service a station in the future. Another expressed gratitude to SpaceX. Thank the Lord for SpaceX. If the factions in Congress and NASA who wanted to give Boeing a non-competitive, sole source contract had had their wish, we'd be in a mell of a hess, as my mother-in-law used to say. So, after all these changes, the uncrewed flight, the financial losses, the revised contract, here's the big question everyone's asking. Is this new plan actually a better deal for taxpayers? Because sure, the changes might make sense for NASA and Boeing. But what about the people footing the bill? Right now, Boeing's commercial crew contract with NASA has a ceiling value of about $4.2 billion under a fixed-price agreement. But here's an important detail. Boeing isn't being prepaid for launches. Funding only gets released as specific milestones are completed. That means there's still roughly $1.4 billion in unobligated funds, money that hasn't been committed yet. So when the number of operational flights goes down, the total cost to NASA should go down too. Fewer flights mean fewer payments, since each mission represents a service NASA buys once it's delivered. And since the upcoming Starliner 1 mission will be uncrewed, it will probably cost less than a normal crewed launch. Crewed flights require extra safety systems, simulations, and support, all expensive stuff. Cargo missions? Much simpler. That said, NASA hasn't publicly shared exactly how much less it'll cost, and that's where the skepticism starts to build. In fact, even some NASA veterans are uneasy about this. One 46-year-old NASA insider put it bluntly, "Can we get confirmation that Starliner 1 is being done at no additional cost to NASA? Unless that's stated explicitly, I, as a 46-year NASA veteran, don't trust that Boeing hasn't rolled NASA on the cost issue." With the International Space Station nearing the end of its life, retirement is expected around 2030. Private companies are racing to fill the void. One of the frontrunners is VAST, which plans to launch its first space station module Haven 1 atop a SpaceX Falcon 9 rocket no earlier than May 2026. Before that milestone, however, the company has a crucial test to complete. A smaller demonstration version of the spacecraft called Haven Demo is expected to launch later this year. The schedule is ambitious, and the company appears determined to stay on track. On October 18th, VAST announced that mission simulations for the Haven Demo are now underway at its Mission Control Center. These simulations serve as full rehearsals, allowing engineers and flight operators to test how the control system's software and hardware interact under mission-like conditions. It's a critical step in verifying that the spacecraft and the people running it are ready for the real thing. Simulations don't mean launch readiness, of course. Several rounds of testing and review still stand between VAST and liftoff, but they do mark one of the final phases of preparation. Once launched, Haven Demo will evaluate a range of flight systems from radiation-hardened computers and sensors to propulsion and communications, helping the company refine designs for Haven 1. If VAST meets its current target, Haven 1 could become the first fully operational commercial space station in orbit. Progress appears steady. Earlier this month, on October 11th, the company reported that the Haven 1 flight article has been painted following completion of its primary structure. The next steps include installing major components such as the hatch and the module's signature domed window. After integration, the spacecraft will undergo pressure and load testing in Mojave, California, essential procedures to confirm it can withstand the rigors of launch and safely sustain astronauts once in orbit. From there, Haven 1 will move into its final stages of preparation, bringing VAST one step closer to realizing its vision of a privately operated space outpost. VAST's first space station will be small, intentionally so. The single-module design serves as a proof of concept, meant to demonstrate that a privately built orbital outpost can operate safely and support human crews for extended periods. Haven 1 is expected to remain in orbit for about 3 years, hosting up to 4 short missions. Each would last roughly 2 weeks and carry a crew of 4 astronauts. Physically, the module is compact. Measuring 4.4 meters, 14.7 feet in diameter, Haven 1 will offer a habitable volume of just 45 cubic meters, 1,500 cubic feet, about the interior space of a city bus. That's roughly 1/8 the volume of the ISS, whose pressurized sections total 388 cubic meters. Inside, VAST aims to make the environment efficient, yet comfortable. The station will feature a 1.2-meter, 4-foot domed window for Earth views, a fold-out communal table private sleeping quarters for each astronaut, and high-speed internet provided by SpaceX's Starlink network. It's not designed to be a luxury hotel, VAST CEO Max Hoyt said. But we believe that in every environment, if you feel better, if you can rest better, and if you can communicate better, then you can work better. After Haven 1 reaches orbit, its first crew will follow a few months later aboard SpaceX's Crew Dragon spacecraft as part of the VAST 1 mission. Once docked, Dragon will remain attached to the station, effectively serving as a second module and backup habitat. For its initial operations, VAST plans to build on research already underway aboard the ISS, particularly in pharmaceutical development and microgravity manufacturing. The company envisions Haven 1 as a focused, streamlined platform for scientific and industrial work smaller and simpler than the ISS, but designed to prove that commercial space stations can deliver meaningful research outcomes without the scale and cost of government-led programs. VAST's decision to partner with SpaceX for its first space station mission was hardly a surprise. Few companies have as much experience in human spaceflight, and the relationship between the two firms runs deep. Many of VAST's senior engineers and managers are SpaceX veterans, which has helped foster an unusually close collaboration. From the start, the two teams worked side by side to ensure Haven 1 would integrate seamlessly with SpaceX's Crew Dragon spacecraft, from structural interfaces to life support and docking systems. SpaceX, after all, has become the world's most reliable provider of crewed launch services. The company remains NASA's sole US-based partner for transporting astronauts to and from the ISS. and Dragon has accumulated a strong track record across multiple missions. The spacecraft's autonomous docking system has been tested repeatedly in orbit, making it a natural fit for Vast's smaller, privately operated outpost. Beyond launch and transport, SpaceX will provide a range of support for Vast's missions. The company is responsible for astronaut training, including instruction on Falcon 9 operations crew, Dragon procedures, emergency protocols, and simulated dockings with Haven 1. During flight, Dragon will do more than just carry the crew. It will supply power communications cargo and additional research capacity while attached to the station. Connectivity will also come via SpaceX's Starlink network, providing high-speed internet access for both mission operations and crew communications. Looking ahead, SpaceX plans to conduct 2 additional Dragon missions to the ISS to support Vast's participation in NASA's private astronaut program, should the company be selected. These flights would give Vast valuable experience managing crewed missions in orbit and strengthen its working relationship with NASA. That experience could prove critical as the company prepares for future stations, including its proposed Haven 2, and seeks a competitive edge in Phase 2 of NASA's Commercial LEO Destinations program. For SpaceX, the partnership with Vast offers benefits of its own. Each Haven mission represents another opportunity to showcase the company's Falcon 9 rocket and Crew Dragon spacecraft in a high-profile commercially funded role, something few other organizations in the world can attempt. Successful operations for private stations could help SpaceX attract additional customers, including NASA and emerging commercial partners, looking to send both people and payloads into orbit. The collaboration also expands the reach of Starlink, SpaceX's global broadband network. Haven 1 will rely on Starlink for high-speed communications, giving the company a chance to demonstrate its internet service in a new, more demanding environment orbital operations. It's an experiment that could open new markets for Starlink and strengthen SpaceX's position not only as a launch provider, but as a complete space infrastructure company. In essence, the arrangement is mutually reinforcing. Vast gains a trusted launch and operations partner with proven human spaceflight experience, while SpaceX cements its role at the center of the growing commercial space ecosystem. The relationship is expected to extend well beyond Haven 1. Vast is already planning a larger follow-on station, Haven 2, which could serve as a more capable, longer-term replacement for the International Space Station. Haven 1 is designed to prove the company's technical and operational credibility, while Haven 2 represents the real goal, a commercial outpost that might one day anchor NASA's post-ISS presence in low Earth orbit, under the agency's Commercial LEO Destinations program. In many ways, Haven 2's a scaled-up, NASA-certified version of Haven 1, designed to be modular, expandable, and built piece by piece in low Earth orbit, much like the ISS before it. If Vast secures a NASA Commercial LEO Destinations contract in 2026, the company plans to launch the first Haven 2 module aboard a Falcon Heavy rocket targeting operational status by 2028. The initial module will measure about 5 meters longer than Haven 1 and nearly double its internal living volume while retaining the same core systems that will have already been proven in orbit. That first 16-foot-long unit is only the beginning. Vast intends to follow with 3 additional modules over the next 2 years, each built to the same efficient, cost-effective design. Together, they will expand the station's usable space, strengthen life support and power capacity, and add new facilities for research and manufacturing. Each new section will offer enhanced payload accommodations while preserving a consistent modular architecture, a deliberate strategy to simplify assembly, reduce costs, and accelerate deployment. Although Haven 2 is a commercial venture, Vast is designing it with international collaboration in mind. That cooperative spirit, after all, was central to the success of the ISS. For more than 2 decades, the ISS has provided scientists with a one-of-a-kind platform to conduct experiments in microgravity. VAST hopes to carry that legacy forward through Haven 2's dedicated laboratory module, the Haven 2 Lab, equipped with advanced facilities for microgravity research and in-space manufacturing. With greater volume and power capacity than Haven 1, the lab will support larger payloads and more complex instruments, offering a flexible environment for scientific and industrial users alike. Between 2030 and 2032, VAST plans to add a 7-meter diameter core module and 4 more Haven 2 units, for a total of 8 Haven 2 units, bringing the station to full operational capability. When complete, Haven 2 will feature a sweeping 12.5-meter wide cupola window, one of the largest ever installed in orbit, offering astronauts panoramic views of Earth and deep space. Each of the station's modules will also include individual 1.1-meter viewing windows for a total of 16 observation ports. Externally, Haven 2 will carry the hardware necessary for serious orbital operations, a robotic arm for payload handling, berthing ports for visiting spacecraft, an external payload airlock, and a dedicated airlock for spacewalks. NASA took a decisive step toward the future of low Earth orbit in 2021 when it launched the commercial LEO Destinations program. The initiative marked a fundamental shift in the agency's approach. Rather than building and operating its own successor to the International Space Station, NASA will instead become a customer purchasing crew, time research access, and services from privately built and operated stations. VAST Space is one of several companies vying to fill that role with its Haven 2 station, but the field is becoming increasingly crowded. Axiom Space Blue, Origin, and Northrop Grumman are each developing their own ISS replacement concepts, creating a highly competitive environment that promises to drive innovation in design, manufacturing, and orbital operations.